Hello friends, this is Dharmin Patel. Welcome to the lecture series of Mathematics-2. In this lecture, we will discuss the initial value problem of the first order, first degree ordinary differential equation. This is a one type of revision lectures. In this lecture, we will revise some methods of previous lectures. Here, first of all, what is the first order, first degree differential equation? So it is of the type m of xy dx plus n of xy dy equal to 0, or it can be rewritten as dy by dx equal to p of xy upon q of xy. Also, we say in the first order first degree homogeneous differential equation, and the homogeneous function is look like f of xy equal to x raised to n phi of y by x, or f of xy equal to y raised to n phi of x by y. In the case of homogeneous differential equation, we assume the y by x equal to v and then solve it by separable variable method. The next point is first order first degree linear differential equation, dy by dx plus p of xy into y equal to qx be a first order first degree linear differential equation, and it is solved by integrating factor. Now, and in the last lecture, we say that dy by dx plus px into y equal to qx y raised to n. It is a first order first degree non-linear differential equation. It is also known as Bernoulli's equation. To solve this differential equation, we convert into the first order first degree linear differential equation by using u equal to y raised to 1 minus n, and then again apply the first order first degree linear method. Now we will see some methods to solve the first order first degree ordinary linear differential equation. Already we studied the separable variable method for the homogeneous differential equation, first order first degree linear differential equation, and first order first degree non-linear differential equations, and how to solve them. Here we will use these methods to solve our initial value problems. First of all, we see the first example. First example is 2x y dx minus x square dy equal to 0. This is our first order first degree ordinary differential equation. Here some conditions is given. So first of all, we concentrate on how to find the solution of this differential equation, and we find the general solution first, and then we use this condition. This condition is known as initial value problem or initial value condition. Here, how to solve this differential equation? So we can solve by homogeneous separable variable method as well as simple separable variable method. Already we did this example in our separable variable method topic. For I am writing direct here general solution. So what is the general solution of differential equation? The general solution of this differential equation is x square equal to yc. It is already solved by separable variable method in the first separable variable method topic. Now we will put our conditions in this general solution and we get the particular solution. That is the use of this initial condition. So here, first of all, what is the meaning of general solution? So it is different types of curves and which satisfies our differential equation. Now for the different value of c, we can get some different curves, but here we want to find some specific curves which satisfies our condition y of minus 2 equal to minus 4 by 3, and it is given condition. So we have to find the particular solution or particular curve which satisfies this condition. Now, how to find it? So first of all, here minus 2 is x value and y value is minus 4 by 3. So we will put x equal to minus 2 and y equal to minus 4 by 3 in the general solution x square equal to yc, and we find the value of c. Then after putting these values in our general solution, we get minus 2 square equal to minus 4 by 3 c, and after solving it we get 4 equal to minus 4 by 3 c. Both 4 cancel from the both sides, then we get c equal to minus 3. So here we can find the particular value of our c, arbitrary constant c, using our initial conditions. Now we will put c equal to minus 3 in our general solution, then we get x square equal to minus 3y be a particular solution of our differential equation. Now we will see the geometrical meaning of this solution. So first of all, we can see here, this is our general solution, x square equal to cy be a general solution of our differential equation, which is already obtained by separable variable method in the separable variable method lecture. You can see it. Now here, after solving this differential equation, we have to find c if initial value conditions is given. Here we have an initial value conditions y of minus 2 equal to minus 4 by 3. Now what is x square equal to yc? So it is a family of some parabolas. Here we can see it. These are some parabolas symmetric to y-axis and passing through origin, and this is a family of parabolas. This is general solution. This is our general solution, x square equal to yc. Now, after putting value of c, which is minus 3, according to our condition, we get particular solution x square equal to minus 3y of our differential equation. And what is the meaning of it? So it is some specific curve which is drawn in the green line. That is x square equal to minus 3y, which is our particular parabola. It is according to our condition. That means that is our concept of initial value problem and particular solution in the first order, first degree ordinary differential equation. Now we will see the second example of initial value problem. Here our initial value problem is x divided by dx plus y square upon x equal to y, with the initial value condition y of 1 equal to 1 by 2. That means when x value is 1, our y value is 1 by 2 in the particular solution. So first of all, we have to find the general solution of this differential equation. Here our differential equation is x divided by dx plus y square upon x equal to y, which is look like a first order, first degree linear differential equation, but it is not a linear differential equation because we have a y square in the second term on left hand side. So it is a Bernoulli's equation or non-linear differential equation. So first of all, we divide both sides by x, then it will be divided by dx plus y square by x square equal to y by x. Now that can be rewrite as divided by dx minus y by x equal to minus y square by x square. That is our proper form of Bernoulli's equation. Now we divide the whole equation by y square, then we get 1 upon y square divided by dx minus y upon xy square equal to 1 minus 1 upon x square. Now we rewrite this equation like 1 upon y square divided by dx minus 1 upon x into y raised to minus 1 equal to minus 1 upon x square. Call it result number 1. To convert this equation into first order, first degree linear differential equation, we take u equal to y raised to 1 minus m, and here m equal to 2, then u equal to y raised to minus 1, and du by dx becomes minus y raised to minus 2 into dy by dx, and this is coming from both sides differentiating with respect to x upon y square divided by dx and put in this in the result number 1. Then we get minus du by dx minus 1 upon u equal to minus 1 upon x square, which is our first order, first degree linear differential equation in x and u. Now take the minus from common from the both sides, then we get du by dx plus 1 upon x u equal to 1 upon x square. First order, first degree linear differential equation. Here px is 1 upon x, qx is 1 upon x square. Now how to solve this first order, first degree linear differential equation? So using integrating factor. So now our integrating factor is e raised to px dx. Here px is 1 upon x, so it is e raised to integration 1 upon x dx. Now integrating factors becomes e raised to log x, and that is equal to only x. So integrating factor is only x. We get general solution of the first order first degree linear differential equation du by dx plus 1 upon x u equal to 1 upon x square is integrating factor into u equal to integration of qx into integrating factor dx plus c or b. Here I am taking the b. So now we can find the solution. Integrating factor is x, u equal to integration of 1 upon x square into x dx plus log c. We are taking b equal to log c here as arbitrary constant. Then finally we get xu equal to integration of 1 upon x dx in plus ln c. Now that is xu equal to log c plus log x, and that can be written as xu equal to ln xc. Now we remove the log from the both sides, and e raised to xu equal to xc. C is arbitrary constant and u is some value of y or some power of y. So we replace the value of y. Here put the y u equal to y raised to minus 1 or y u equal to 1 upon y in our solution. E raised to xu equal to xc. Then we get e raised to x by y equal to x into c be a general solution of our differential equation. Here c is arbitrary constant. Now we use the initial value condition because we have a general solution e raised to x by y equal to xc be a general solution, and we want to find the particular solution according to the initial value condition. Initial value condition is y of 1 equal to 1 by 2. So our x is 1 and y is 1 by 2. Put in this general solution e raised to x by y equal to xc and find the value of c. So we will put x equal to 1 and y equal to 1 by 2. Then finally we get c's value is e square. Then put this value c equal to e square in our general solution e raised to y by x equal to xc. Then finally we get e raised to y by x equal to x e square be a particular solution of our differential equation x divided by dx plus y square upon x equal to y. Here first of all we convert our Bernoulli's equation into the first order first degree linear differential equation and then solve the linear differential equation by integrating factor, and after solving this we use the initial value conditions which is given in the question x equal to 1 and y equal to 1 by 2 and find the particular value of c. Then we get the particular solution of our differential equation. So that is the method to solve the initial value problem. Here remember that first of all we find out the general solution by well-known methods. Then we use the initial value conditions. Initial value conditions gives our value of x and y. That means our curve is passing through particular point and we find the particular value of c from that condition and put this c value in our general solution, and then we get the particular solution of the differential equation. It is called a particular curve from the family of curves. So that is the method to find the initial value problem. Thank you very much.